Welcome back, students, to lecture 1 part 2. In this lecture we're going to be looking at inequalities and absolute values where we solve both graphs and equations. Okay, looking at this first example, x over 4 is less than or equal to 9 over x. I hope you'd all say to me, don't multiply through by the x term. Never ever lose that denominator, because when multiplying by the x, and of course we don't know the sign of x, we don't know what effect that would have on the inequality sign and its direction. So we never ever lose that denominator. So over here, I've just pushed the slide on a little bit. We take the 9 over x to the left-hand side. We form the LCD, which is going to be 4x. Obviously manipulate and adjust the numerators, and then we go and factorize. Remember, we always go and factorize so that we can go and find our critical values. Remember, the critical values are the zeros of the expression, and therefore on either side of the zeros our signs are changing, which is then going to help us determine where the expression is either positive or negative in this case. Just another important point that we must just remember, this 0 over here, this critical value of x is equal to 0, whilst we're including, because this inequality says include, we can never include that because it's a denominator, and then our expression would be undefined. So just have a look and see how I set this out. It's a good idea to use an open circle, because you know that's where the 0 of the denominator would have made the expression undefined. All the other zeros are perfectly acceptable. And then you do your normal table of signs. This table of signs we learned in grade 11 in core mathematics. We're being asked to find the negative solution set, so we go and find where it's negative there between 0 and 6, it's negative to the left of negative 6, and then we go and represent, and remember we weren't including the 0. Here's another example. Before you go anywhere, go and factorize. Factorize the numerator, factorize the denominator, so that you can go and get your critical values. Okay. The interesting thing here at the top is that we're going to get a bracket squared. Please remember that any bracket squared will always return a positive. So in actual fact, that doesn't really affect the signs in our sign table or our number line. But there is a 0, and that 0 is negative 2. Something else that we're going to notice in this example and the example that follows is that the signs on either side of this critical value, so this critical value over here would be negative 2. The signs on either side are going to be exactly the same. Recognize that and notice that, and don't be too quick to just write a whole lot of alternating signs. These signs will be the same on either side. Again, critical value of 0, a critical value of 4, and a critical value of negative 4 may not form part of the solution set, because these critical values make the expression undefined. And then again, put everything together. Remember, this is where it's undefined, undefined, and undefined. And also notice over here at the negative 2, these signs are the same on either side. So take your table of values, go and substitute different values, and you will notice between 0 and negative 2 it's positive, and then on the other side of this critical value, again, it's positive. Now we wanted the negative solution, so we would select there and we would select there, but be very careful, because in doing that and that we've lost a solution. Remember that this negative 2 is also part of our solution set. Okay, because we were being asked where is this inequality less than or equal to 0, so any zeros must also be part of the solution set. And then here, if we just put all the tricky rickies together, look at this first expression here at the top. Please remember that that cannot give you any zeros in the real number system, because x squared is a positive, adding to 4, that will always just be a positive. We can just ignore that entirely. We know that x equals 1 is a critical value. We know that x equals minus 2 is a critical value. We know that negative 3 is a critical value, but that negative 3 cannot form part of the solution set. The second point, because this is a square, remember that the signs on either side of the critical value will be exactly the same. The signs don't change. And then we just put on the number line. There's my negative 3 where it was undefined. Put on all your values. We want the positive solution set. We want the positive solution set. Obviously, this positive solution set must, of course, exclude the negative 3. Okay, so the inequalities are not too difficult. Just remember, never ever multiply through by a variable. You've just got to form an LCD. Then it's all about factorizing, finding critical values, putting them on a number line. Let's look at some absolute values. So the graphs, we're going to divide them into 4 different categories. First of all is the classic V-shaped absolute value graph. Okay, and that is very similar in concept to the quadratic equation or quadratic function. Remember, we've got in a parabola, the turning point would be PQ. Here, our salient point is also going to be PQ. Hopefully, you see the similarities to the quadratic. You would have had y equals a x minus p all squared plus q. And if you had to explain to me why they're quite similar, hopefully you'd say, well, the absolute value always returns a positive. This bracket squared always returns a positive. So there's going to be lots of similarities and parallels between the two graphs. Then, of course, we look at y is equal to the absolute value of f of x, remembering that the absolute value will always return a positive. So we can draw f of x and then say to ourselves, anything below the x-axis must be reflected above because we're returning a positive, and we'll look at an example of that just now. And then what happens when we're adding different parts, making up a function where there is an absolute value component and something that isn't an absolute value. And my advice there is to stick to the definition. So we say to ourselves, we either have a positive inside the absolute value or we have a negative inside the absolute value, and then we treat each of those for their own defined domain. Okay. And then finally, one that we don't see too often, this is a bit of a curveball. I've rarely seen this being asked in matric finals. If you've got f of the absolute value of x, again, don't panic, treat it according to the definition. So you say to yourself, it's either f of x or the f of negative x, okay, based on our restricted domain. Let's look at a few examples briefly. So here is that standard V-shaped absolute value. And I want you to look at this and say, well, it's a negative. Just like the parabola, it would have been unhappy. So it's got that classic V shape. Then just go through your steps. What would we do? Y-intercept, x-intercept, and of course the turning point, which in this case, we've got a salient point. So my salient point is 3, 5. If I go and find the y-intercept, making x equals to 0, you're going to get negative 2 times absolute value of negative 3. Remember that returns a positive 3, so negative 6 plus 5 is negative 1. And then I've gone here and set it out. There's so many different ways of setting it out, but based on the definition, I've said, well, the inside of the absolute value was positive, or the inside could have also been negative. And then solving those two basic linear equations, I will get x-intercepts of 5, 5 and 0, 5. And then put all of that together, and you've got your classic shape graph. I'm going to re-look at this graph, but I'm going to unpack it based on the definition, because sometimes you will get something that doesn't look familiar at all, and you say to yourself, gee whiz, what will I do? And my advice is you just unpack it according to the definition and your understanding of split functions or composite functions. So if I looked at this graph again from scratch, so I started from scratch, I could say, well, the inside here is positive. X minus 3 is greater than or equals to 0. That means then that x is greater than or equal to 3. This now becomes the domain for my new graph. And I substitute in saying, well, this was positive, and when I multiply out, I'm actually drawing this graph for x is greater than or equals to 3. So I'm seeing that graph to the right of this line, which is x is equal to 3. So this right-hand side decreasing function, y is equal to negative 2x plus 11, is just the function I would have drawn on the right-hand side to the right of x is equal to 3, because that was its domain. And putting 3 in here, if I substituted x was equal to 3 to find the y value, negative 2 times 3 is negative 6 plus 11 is 5. And so then I would have been drawing this straight line, y equals negative 2x plus 11, to the right of 3, knowing that its endpoint here is 3, 5. And then in a similar way, we say to ourselves, well, the inside could have also been negative. This part of the absolute value here could have been negative for where x is less than 3. So now I'm drawing to the left-hand side here. Make this expression or this part negative, and we realize that we're drawing this graph here, y is equal to 2x minus 1. So the two straight line functions are forming the absolute value function. But really, it's like having a split function. I'm drawing this negative 2x plus 11 for the domain x is greater than or equal to 3. And then this domain here for x is less than 3, I'm drawing y equals 2x minus 1. And again, finding x-intercepts and y-intercept is equally easy. Here, 5b from your worksheets, this is a standard absolute value graph. Well, actually, before I even get there, inside this f of x is a standard grade 11 function. This is a hyperbola. You are very comfortable and familiar with this. Okay, so if we just look at the graph and we sketch f of x, we should notice that there is a vertical asymptote at -1, there is a horizontal asymptote at -4, and we can go and draw this graph quite easily. Remember that when we take the absolute value of this function, so it's slightly different to the absolute value graph, it's the absolute value of a graph. We know that we want to return a positive. We are always going to return a positive. So anything that is above will not change, but anything that is below will change. Now I'm going to toggle between these two screens, so just see what happens. I'm there. Let me go back again. So over here, we should be noticing that the part that goes underneath will reflect above. The part that is underneath over here on the left will reflect above. But the really cool thing is that over here, this horizontal asymptote of -4, when you take the absolute value, that asymptote also reflects above. So I then get over there this horizontal asymptote of 4. Okay, so we see the green is the original graph and the blue is just where I've gone and reflected it above, and this blue over here is where I've reflected it above. So I can give you any function and you just go and draw the normal sketch of f of x and then remember to reflect that part underneath above. And then here we're going to be drawing absolute value where I've got a function added or subtracted or somehow combined with the absolute value. And so my advice is stick with the definition. So what I mean by the definition, I'd say to myself, well, this inside here could have been positive. So you're drawing y equals x minus 2, and therefore y is -2, which is how I get this function. But we've got to remember that we are doing this for where x is greater than or equal to 0. So you have got a restricted domain. You have got a split function. I'm drawing this horizontal line y equals 2 for x greater than 0, greater than or equal to 0. And then if I just look at the second part where this inside now could have been negative, so you would have had y equals x minus the negative of x, and this negative makes it positive, so you're going to see 2x plus 2, and then we're saying to ourselves, well, we're drawing this straight line graph, y equals 2x plus 2, where x is less than 0. So all you're doing is you're drawing two different functions, okay, for different domains. And then when we put that all together, it's not too difficult at all. I'm drawing the horizontal line y equals 2, to the right is 0, and I'm drawing y equals 2x plus 2, which then is going to have a y-intercept of 2, an x-intercept of -1, draw that straight line, and that is to the left of 0, and Bob's your auntie. And then let's look at a couple of equations. And all these equations are based on the standard definition. So just remember, if you've got an absolute value equals to a constant, that absolute value could have either been positive or negative. But of course, if it's not a constant and there are x parts over here, we've got to be quite careful. And this is an example to illustrate the point I was just making. So we say to ourselves, we've got two options. This inside is positive or this inside is negative. And so split your solution right from the outset. And I say, well, that inside could have been positive, or that inside could have then been negative. And then you go and solve for each of these things. So I'm going to say, okay, well, if the inside was then positive, that would have meant that x had to be greater than or equal to -5. And then I go and solve, and I get x is 15. And what we recognize is that 15 is so definitely greater than -5, and therefore it satisfies the interval in which we're working. If I go to this right-hand side over here, for where x plus 5 is less than 0, in other words, x must be less than -5, make the inside negative, go and solve, and I get an answer of 5/3. But 5/3 is definitely not less than -5, and therefore we go and reject the solution. So please remember that, again, I'm working directly from the definition. I'm restricting the domain and saying these solutions have to satisfy the domain from which we are working. Some teachers won't set it out like this, and that's perfectly acceptable. Um, and what those teachers will say to you is you don't have to actually go and play with the domain, but you definitely have to check each of the answers. So check the validity of your answer. And when you substitute them back into the left and the right hand side, you would have found out that 15 definitely works, but 5/3 didn't work. The equation wasn't balanced. So you can either check your solutions at the end, or you can actually base it on the definition. And then the last thing that we've got to do is look at absolute value inequalities. Now, there are a couple of clever tricks. I'd like you to look at this clever trick. You may have come across the word Gorland. This is something really quite clever. If something is greater than, there is going to be an or. If something is less than, there is going to be an and. So if I'm less than, you know that this is going to be between the negative c and the c. But if I'm greater than, it's either going to be greater than or it's going to be less than the negative. So for example, here I know that this x plus 6, if it's less than or land, it's an and, it's between something and something else. So it's just between the negative 8 and the 8, and then I can go and solve. But the good news is the absolute value inequalities that we have to solve in the exam are always going to be based on sketches. So more often than not, the examiner is going to ask you to draw a sketch and then ask you to solve an absolute value based on that sketch. If they don't, and for example, they said go and solve this, then you know it is based on a sketch, and you go and draw these two graphs. So I would draw the absolute value of x plus 6, and I know I'm getting this classic kind of V shape, and this over here. So I've actually got two graphs. I've got y is equal to this absolute value, and y is equal to 8, which is very easy, and that's my horizontal line. And then I'm saying, well, where is the absolute value beneath that line? So you're just using your knowledge of your core skills, your graph skills, saying where is the absolute value beneath? So if I just go down, here we go. So 2, and if I just go down over here at negative 14, the absolute value is going to be less than between negative 14 and 2. All right, that's taken us to the end of part 2. We'll return just now with part 3 of lecture 1.